Good morning, everyone. Thanks for joining us again for the third day of the Winter School on Advances in Secure Computation. So the first speaker of today is Yuval Ishai, who's a professor of computer science at the Technion. He did his PhD also at the Technion, and then he went on to be a postdoc at Dymax Center and AT&T Labs Research and Princeton University. And he also spent 2 extended sabbaticals at UCLA. So Yuval has worked on many areas of cryptography and also on the interconnections with computational complexity. But his works focus mainly on secure multi-party computation and efficient proof systems. And he's received multiple Best Paper Awards and also the TCC Test of Time Award, and he's a 2018 Fellow of the IACR. So we're very fortunate to have Yuval join us today and tell us a little bit about pseudorandom correlation generators.
Okay, thanks a lot, Mo, for the introduction, and I'd like to thank the organizers, Mo and Kermit and Benny, for organizing this great school. It's been fun to attend and hopefully also fun to participate on the other side as a lecturer. Okay, so I'm going to talk today about a notion called pseudorandom correlation generators. The talk is mainly based on a recent line of works with Elet Boyle, Shofua Couto, Niv Gilboa, Lisa Cole, and Peter Scholl, but I'll also cover some older work and some more recent work in the area. Okay, so let me start with a roadmap, which is actually not a roadmap for this talk, but it's a slide stolen from a talk given almost 20 years ago at Crypto 2003. This was actually, it's a surprise that PowerPoint can still process slides from 2003, but this was the opening slide of the Extending Oblivious Transfers Efficiently paper. And the goal there, as the picture may suggest, was to have a large-scale, efficient way of generating many oblivious transfers, which, as we heard, is a useful building block for secure computation protocols. The main goal of this work was to amortize away the costly use of public key cryptography and mainly reduce the computational cost of oblivious transfers to be essentially that of symmetric encryption. This was the goal, and this is why such OT extension protocols are still used even today as a fast way to get this useful resource for secure computation. However, despite the big performance improvement, this OT generation technique is still quite noisy in the sense that it involves a lot of communication. So even if we just want to generate random OTs or bit OTs, which are useful for many applications, we still need to communicate over 100 bits per OT, which can be a lot and can be an efficiency bottleneck, as we will see. So, in the spirit of today, back at the time, we did not know much about the environment, and now we want to have a more environmentally friendly way of the same. So we want to have a so-called silent way of generating OTs that uses only a small amount of communication. And in fact, not only OTs, but we will also want to generate other kinds of useful correlations, such as vector oblivious linear evaluation that we heard a lot about from Peter yesterday, and more. And in the first part, in the first hour of this lecture, I will start with a broader motivation, definitions, and low-end constructions from symmetric cryptography. And then in the second part of the talk, I will get to actually this silent OT generation, Vole and other correlations based on the learning party with noise assumption. Okay, and of course, feel free to interrupt me with questions at any time. Okay, and I should say that tomorrow Peter will give 2 more talks about PCGs that we'll sometimes refer to from today's lectures. Okay, so let me start with some background and motivation. So recall these familiar characters, Alice and Bob, that you've seen in Alet's and Peter's talks in the previous days. So in the basic setting of secure two-party computation, they each hold a secret input, and their goal is to learn some publicly known function f on their inputs without revealing anything else to each other. Okay, in this talk, we will also consider protocols involving more than two parties, but the baseline setting will be two-party computation. And to this end, Alice and Bob exchange messages that reveal the desired output and don't reveal anything else about the input. Okay, so let's give an overview of different ways we have today, the main different approaches for solving this problem, focusing again for now on two parties with semi-honest security, or also known as passive security. So the first approach, due to Yao, uses garbled circuits. They achieve minimal latency, so the round complexity can be a small constant or even minimal. The downside is that this approach is only concretely efficient for Boolean circuits, and even for Boolean circuits, it involves quite a lot of communication, again, over 100 bits per nonlinear gate, AND or OR gate. Okay, the next approach is due to Goldreich, Micali, and Richardson, also known as the GMW paradigm or approach. And here, the protocols take more rounds. The number of rounds is proportional to the depth of a circuit. And they work by repeatedly using a basic primitive, oblivious transfer in the case of Boolean circuits, for converting linear shares, or in the two-party case, just additive shares or XOR shares of, say, an AND gate, of the inputs of an AND gate to additive shares of the output of an AND gate using a couple of OTs. So I will talk more about the concrete efficiency of this approach, but the disadvantage over garbled circuits is that the round complexity is not constant, so this is bad when you have high latency networks. But the bright side is that there is a potential, for instance, if the OTs are pre-computed, we'll talk about that later, then the communication complexity can be much smaller, by 2 orders of magnitude, than garbled circuits. And moreover, this approach can also extend to arithmetic circuits in a natural way. A much more recent approach that we have since 2009 is to use fully homomorphic encryption. Here it's kind of a one-shot solution. It breaks the circuit size barrier, unlike the previous two solutions, so the communication complexity can be proportional to the input size rather than the circuit size. And the main downside of this approach is high computational cost. And also for small inputs, there is quite a big concrete communication cost, even though it's asymptotically almost optimal. The most recent approach is the secret sharing analog of fully homomorphic encryption. This is the dual notion of function secret sharing that Let talked about on Sunday. And here the idea is that instead of encrypting my input, the parties just secret share their inputs and then locally evaluate the function on their shares. If you use the right kind of secret sharing scheme, this can give us directly, without any further communication, additive shares of the output that can be exchanged to recover the output. Okay, so just to remind you, this is really the same as function secret sharing, except that we reverse the role of the function and the input. In function secret sharing, we split the function. Here we split the input. So the advantage of homomorphic secret sharing over fully homomorphic encryption is that, at least for simple types of functions, as we've seen in the Let's talk, We have much more efficient solutions, and we also have solutions under more diverse set of assumptions, again, for functions in restricted classes. And the disadvantage over fully homomorphic encryption is that communication here is inherently proportional to the sum of the size of the inputs, whereas in FHE, it's the size of the shorter input. So in case of unbalanced inputs, FHE is better in terms of communication. Okay, so this is just an overview of 4 different approaches. And homomorphic secret sharing is really the one that is most related to this talk. So let me give a bit of an overview again, just essentially repeating something that you've seen in Let's Talk if you attended it. This is a picture of where we stand in terms of HSS schemes for different types of classes of functions. And on the high end, can you see the pointer? The mouse, okay. On the high end, if we use specific kinds of fully homomorphic encryption, we can handle general circuits. This is LWE plus because we need some circular security assumption. On the low end, if we're not willing to make any cryptographic assumptions, then we can only deal with linear functions. And in between is the more recent and more interesting stuff. We will hear from Peter a lot about the cryptomania part, which is very interesting, practically feasible, but not very practically efficient. And for today, the type of HSS constructions or the dual FSS constructions that are most relevant are the ones in minicrypt based on symmetric crypto that we heard a lot about on Sunday from Elet. And also something that we'll hear for the first time about today is constructions that rely on the learning, different flavors of the learning party with noise assumption that we refer to as a Lapland, as a short version, to a world where such assumptions exist. Okay, so to focus our motivation, let's consider a very concrete challenge. So from a concrete efficiency perspective, the fastest secure computation protocols are in the honest majority setting, and specifically the easiest case is that of 3 parties. Again, for now, we consider semi-honest parties. And of these 3 parties, at most 1 is corrupted. This is really the easiest setting for secure computation where the most practical protocols exist. What is the state of the art today for Boolean circuits in this setting? Well, XOR gates or NOT gates are for free. And if you want to do something like an AND or an OR gate, the communication cost is that every party needs to send 1 bit. Okay, so that's the communication cost. It's linear in the circuit size, but really just linear in the number of nonlinear gates in the circuits, but really just 1 bit per gate, per party. And computation is even cheaper. So it's only, you need to use a pseudorandom generator to get this communication complexity, but really in a practical setting, the overall performance will be dominated by communication and not by computation. Okay, and these protocols are super fast and they're even being deployed. So a dream goal for secure 2-party computation, or more generally, secure computation with a dishonest majority, is to get the same kind of performance, right? This seemed like a very far-fetched goal up to a few years ago. This is really our motivating goal, to get protocols in the 2-party or dishonest majority setting that are as fast or almost as fast as protocols in the honest majority setting. Okay, so why does this goal seem challenging? Well, let's look at the approaches we have. If we want to have good communication, in fact, even better than 1 bit per party per gate, because we can get, at least asymptotically, when the circuit size is much bigger than the input, we can use FHE or HSS to get great communication complexity, but this comes at the expense of heavy computation which will become a bottleneck and give an overall performance which is much worse than the 3PC case. If we try to use the more classical approaches of YAO and GMW, right, that's garbled circuits and linear secret sharing based protocols, together with the classical, OT extension techniques, then computation will be okay, comparable to the previous protocol, but then communication becomes worse by 2 orders of magnitude. Okay, so this is really where we stood until recently, and the goal is to bridge this gap. And in fact, we already knew how to bridge this gap in a setting where we have a trusted dealer that gives correlated randomness to the parties. So this setting is kind of like a 3PC setting where one of the parties is offline, okay, and only sends messages before the protocol begins. So we already heard about it. In fact, this slide is stolen from previous talks. And the same Alice and Bob characters will be used throughout this talk as well. So we already heard also, especially in a Let's Talk, that using this trusted dealer, we can handle not only standard Boolean and arithmetic circuits, but also if we use so-called FSS gates, we can handle fancier types of circuits with all kinds of nonlinear gates like ReLU and so on. But for now, let's focus on the case of basic Boolean or arithmetic circuits. And in this case, the online phase is really, after the inputs are known, that's what we execute the online phase. It is really as efficient as, or even can be slightly more efficient than the 3PC protocol with an honest majority. So this online phase in particular can be information theoretically secure. And it can have a constant computational overhead in the sense that securely evaluating an arithmetic or Boolean circuit really takes as much computation or can be implemented by circuits of the same size as the original function up to a small multiplicative constant. Okay, so in some sense, if we look at, if we have very fast communication links, then we can say that the gap between securely evaluating a function and insecurely evaluating a function is a small multiplicative constant. And this is also fast in practice, not only in theory. And indeed, this approach has been the topic of a big body of work originating from Beaver in the semi-honest setting, and the Speeds line of work in the malicious setting. And these works try to optimize different aspects of this offline-online approach of a fast online secure computation using correlated randomness. The main problem with this approach is that if we don't want to rely on a trusted dealer, we need to securely realize the correlated randomness by using some interactive preprocessing protocol, which typically becomes a huge efficiency bottleneck. And in particular, the cost, both in terms of communication and computation of this offline preprocessing protocol is bigger by orders of magnitude than the online cost. Okay, so this is really the bottleneck in this kind of protocols. And the goal of a pseudorandom correlation generator is to kind of minimize this bottleneck. So instead of having these long correlations that are typically as big as the circuit we want to compute, we want to compress the correlation into a pair of correlated keys, K0 or seeds, K0 and K1. Okay, you can think of it as a natural two-party extension of a standard pseudorandom generator. So a standard pseudorandom generator stretches a short seed into a long output that looks random. So really for the purpose of secure computation, it is not enough. In fact, it's trivial to just generate a pair of long correlated strings. You can just use identical seeds of a standard pseudorandom generator for that. The challenge is to really arrange the correlation between seeds in a way that Alice's seed does not give her more information about Bob's expanded output than what the ideal correlation, target correlation allows. Okay, so we'll get more about formalizing that later, but we really want the process to emulate the trusted dealer from the point of view of a corrupted insider, either Alice or Bob. Okay, and this naturally extends, everything I say naturally extends to the multi-party setting. Okay, so this is the goal, that we are indistinguishable from the target correlation, also from the point of view of insiders. Is it okay? Can I go on? Or any questions up to this point?
No questions.
Okay, great. So if we have such a magical object, this gives rise to a new paradigm for secure computation that we call secure computation with silent preprocessing. Okay, so normally we just have an offline phase and an online phase, and now the offline phase is split into two parts. In the first part, we run a secure protocol for emulating this small dealer that generates the short correlated PCG seeds. So this is a setup phase, which we expect, at least from an asymptotic point of view, we expect it to be cheap, both in terms of communication and computation, because the overall circuit complexity of generating the PCG seeds is sublinear in the output size. So at least from an asymptotic point of view, this setup is cheap and is dominated by the other parts. The second offline phase is the silent seed expansion. So you can think of phase one as taking place long before parties expect to run a secure computation protocol. And phase two, the silent local expansion, so we can keep these compressed correlations in the form of PCG seeds. Yeah, I can hear. Can you mute yourself? I can hear background noise. Okay, the second phase is done, say, a day before, or a minute before, or even a second before we know that we want to start doing secure computation. So before the moment when the online inputs come and we want to do secure computation on them, we can just unpackage these compressed seeds locally. This is done without any communication. And only requires local computation. This is the seed expansion part. And finally, the third phase, which is fast and non-cryptographic, is just the same as in the traditional approach of MPC with preprocessing. Okay, so if we look at the total communication and the online computation, then we meet the previous challenge of matching the honest majority case, right? Because the phase one does not have an impact on, at least from an asymptotic point of view, on the online communication, and also not on online computation. And so the only part, and phase two does not involve any communication, so the only potential bottleneck is this expansion. And if we can make this expansion run fast enough, then even if we consider the total, without offline online, just the total cost of such a protocol, then it can meet the motivating challenge. Okay, so really the bottleneck here is the computational cost of expand from an asymptotic point of view, if we consider the protocol as an end-to-end protocol without separating between offline and online. And another nice feature of this approach is that we only, in the case of security against malicious parties, we only need to protect phase one, which is again a small computation, because if the seeds are generated correctly, then in phase two, there is no cheating space, right? If I cheat in what I do locally, I can emulate it by cheating in the online protocol. So if the online protocol is secure against malicious parties given some trusted correlations, say authenticated multiplication triples, then we just need to protect the setup protocol against malicious parties, and the bulk work of expansion is automatically secure against malicious parties. So in a sense, the overhead of achieving security of the offline phase in the presence of malicious parties vanishes. It's not even a multiplicative constant, it's just some additive sublinear term. That's the extra cost of protecting the offline phase against malicious parties, which is again in sharp contrast to traditional approaches where a lot of extra work, computation, communication needs to be done to protect against malicious parties. Cool, and another nice thing about this pre-processing phase, right, the setup phase, is that it can be thought of as exchanging business cards, right? So I can meet someone and we say, okay, maybe we'll want to do some big secure computation in the future. So let's do this cheap exchange of correlated seeds or generation of correlated seeds. It doesn't take a lot of storage. It doesn't take a lot of interaction. It doesn't have a lot of communication. It doesn't have a big footprint in the sense of a traffic analysis revealing that we're up to something. And also you can bluff, right? You can say, hey, it would be nice to do this secure computation in the future. I don't need to really invest a lot of resources in just convincing you that, or trying to convince you that I'm serious about it. And in fact, even one party can expand this correlated randomness, anticipating to do secure computation tomorrow, and the other parties can say, no, I know I don't want to, and doesn't even reveal that they don't want to do secure computation. So it's very flexible, and it allows us this lightweight setup for potential future interactions, even before we know whether they will materialize or not. So for the purpose of this talk, we will just assume the setup phase to be cheap. And Peter tomorrow will talk about different ways of realizing the PCG setup concretely. But for now, let me mention another point about, this is a more definition-oriented point, right? When we say that the online protocol is non-cryptographic, it is not clear what it means, because end-to-end, the protocol is not information theoretically secure. The protocol uses cryptography. How do I define not using cryptography? I cannot even refer to information theoretic security of the protocol, even if you erase the history of the setup. The correlated randomness that we get is only pseudo-randomness, so a computationally unbounded adversary can break the protocol even if we erase the history and just keep the correlated randomness. So what do I mean by saying that the online protocol is non-cryptographic? And, maybe the best answer is that you know it when you see it, right? When you see something that is non-cryptographic, you can tell, but there are ways to formalize it. So we can refer to asymptotic or concrete efficiency of the protocols, which again, as I said, this constant overhead feature, or very, very small concrete constant overhead is something that we don't know how to get for normal protocols in the computational setting. But if you really want to formalize what it means to have a non-cryptographic online phase, you can consider the following definition. So the definition says the following: the online phase is non-cryptographic if, when you erase the history that generated the correlated randomness, you can swap the correlated randomness by something that's computationally indistinguishable, and then in this swapped game, you get information theoretic security. Okay, so we're indistinguishable from a transcript that has information theoretic security. So that's just a theory-oriented point about definitions. And in fact, this non-cryptographic online phase distinguishes from a theory perspective this PCG-based approach from other approaches that are offline-online, like ones based on a laconic secure function evaluation. Okay, so this approach is not competitive from a practical point of view, But if you want to distinguish the PCG-based approach from this approach, from the point of view of a theorem statement, this laconic SFE approach does not give us a non-cryptographic online phase. Okay, so let me switch to talk, since I started talking about formal definitions, let me continue. So our main goal is to formalize what it means, what the notion of PCG for given target correlation means. So a natural attempt is to just consider, so recall that in the basic setting of a PCG, we have a dealer that sends to Alice and Bob a pair of correlated seeds, K0 and K1. And a natural approach for defining the security of such a PRG would be to just instantiate the typical simulation-based definitions for secure computation. So we can think of this protocol where the dealer sends two seeds to the parties and the parties locally expand them as a secure protocol that realizes the randomized functionality that just samples from the ideal target correlation, R0, R1. Okay, and if you spell out what the general definition of secure computation would say for this case of a randomized sampling functionality, it basically says that there exists an efficient simulator that, let me not even try to parse it. This is just, what the definition says. And the main point is that this definition, while it is good for all applications, so by the composition theorem of secure computation, realizing these definitions means that in any application that consumes correlated randomness, we can swap the PCG instead. So that's great. However, it is not hard to see that this definition is not realizable even for very simple correlations, like even if the target correlation consists of two long identical random strings. Okay, and the intuitive reason that this definition is not realizable is that when I get this short seed, okay, so consider a protocol where the dealer sends a pair of identical seeds to the two parties of a standard PRG and the parties locally expand it. Why is this not a fully secure way of realizing a target correlation that consists of two long random strings? The reason is that one party gets a short explanation for the output of the other party, which it cannot get in an ideal experiment where you just get the long random string. Okay, so this is not a technicality. One could come up with typically contrived applications where this type of insecurity makes a difference, right? You can place a bet. Hey, I can explain the output. Alice can say, hey, I can explain the output of Bob by giving a PRG seed. So she can win this bet only in the PCG-based protocol and not in a protocol that uses an ideal long correlation. Okay, so that's bad. However, it turns out that we can slightly tweak the standard real ideal definition in a way that will be realizable and good for almost all applications. And you can think of it, maybe let me not get too much into the details here, but essentially we consider the same real experiment where we take, this is for the case where Alice is corrupted. So we look at the view of the corrupted party, so just the short seed she gets from the dealer, together with the output of Bob, the uncorrupted party, in the real experiment, right, where the dealer sends a pair of correlated seeds and the parties expand them. This is really the real execution. And now we modify the ideal execution to some kind of a game-based definition which captures the informal requirement that the view of Alice doesn't give her more information about the output of Bob. So here we need some reverse sampling condition for this to be defined, which is okay for the type of correlations we will be interested in. But we basically say that condition on the seed that Alice gets, if you condition on the expansion of these seeds, then the output of Bob is the same as we expect from the ideal correlation. Okay, so I will give a slightly more intuitive version for a PCG protocol. So a PCG protocol is something that captures both the setup and the expansion, right? So it's an end-to-end protocol that generates this long ideal correlation using low communication complexity. And the relaxation of the ideal functionality that we consider is the so-called corruptible version of the ideal correlation, which differs from the ideal correlation by allowing the corrupted party to choose its own output. So the corrupted party, say in this case it's Alice, the corrupted party chooses the sample from R0, so it's not random, but it's adversarially controlled, but then conditioned on this R0 chosen by the corrupted Alice, in the ideal model, Bob gets a true sample from the conditional distribution of R1 conditioned on this adversarially chosen R0. And the reason, okay, so now this is the definition, and all the constructions I will describe realize this definition. Why is this definition useful? So it's useful because now we just need to argue that for the purpose of the application that consumes the target correlation, it is okay, it is still secure if we replace the ideal correlation by the corruptible ideal correlation. And the reason this is okay for standard protocols like Beaver, Speeds, and so on, is that the adversary gets no advantage by picking R0, because R0 is just a share of some secrets. As long as the secrets are picked at random and are not known to the adversary has no advantage by picking its own shares of the secrets. Okay, that's the intuition for why this switch from ideal correlation to corruptible version of ideal correlation does not hurt the applications that consume the correlated randomness. Okay, so to conclude, PCGs for almost all practical purposes are as good as ideal sources of correlated randomness. Okay, and I should say that this definition also extends to N parties. And this definition of a PCG protocol, by the way, it is realized, so you can take a PCG according to the previous game-based definition, and if you run a secure protocol for generating the correlated seeds and then apply local expansion of a PCG, then you get a PCG protocol, but in fact, this definition is relaxed. It can be satisfied without securely generating the seeds. Okay, so in fact, in Peter's talk, it will cover some setup protocol that actually uses this relaxation. Okay, questions. So now we start talking about concrete correlations and constructions.
I had one question.
Yeah.
Just a second. So regarding the non-cryptographic online phase, my question is, how is this different from computational security that we already know?
Yeah, so the non-cryptographic means that it's not information theoretic because, the correlated randomness is just pseudo-randomness. However, you can swap it with something that's computationally indistinguishable, right? So really the ideal version of the correlated randomness is computationally indistinguishable from this PCG generated version. And given this ideal version, everything is information theoretically secure. So you can basically generate a fake transcript, which is indistinguishable from the real transcript, where in the fake transcript, no information is leaked in the information theoretic sense. But yeah, that's the difference between the non-cryptographic online phase and just the standard, say FHE-based protocol. We cannot achieve something like this.
Okay, that's it.
Okay, thank you. Good. So let me introduce the cast of characters that will also, in the rest of this hour and the next hour, we'll talk about them a lot. So we've seen some of them, but here is something that we haven't seen so far in this school. We will also consider multi-party correlations. And here, a very useful type of correlations, specifically for honest majority secure computation, is so-called linear correlation. A linear correlation is one where the parties jointly hold a random vector in a linear space. So it's related to Henry's talks about secure analytics. So we consider think of it as some linear secret sharing of a random secret. That's a typical form of linear correlation. And again, this ideal correlation is long, so we consider n instances of additive sharing of 0 over some abelian group, or n instances of degree t Shamir secret sharing of a random secrets over some finite field, and so on. Okay, so this is something that we'd like to generate using PCGs. Applications include verifiable secret sharing, honest majority MPC, proactive secret sharing, aggregation, and so on. Let me briefly give two representative applications. So suppose that we have parties that want to securely aggregate or add up their inputs. So if we have additive shares of 0, if the parties hold additive shares of 0, then they can do it in a simple and non-interactive way by having each party just communicate to the outside world the input XORed with the corresponding random input, and then the messages together, they reveal the sum of all inputs and don't reveal any other information. So that's a very simple form of aggregation that can be made more efficient by using PCG for many additive shares of 0. Another example, now this refers to Shamir secret sharing of a random secret. Suppose that the client wants to secret share using Shamir scheme some secret X between a bunch of servers. The reason the client wants Shamir secret sharing rather than additive secret sharing is for robustness. And it also wants some homomorphic. Shamir is also useful for homomorphic properties and so on. So the naive way of doing it is by just generating a share for each server and sending either one share to each server, or you can send all shares encrypted to one server and ask him to route it to the other servers. In any case, the client's communication here scales linearly with the number of servers. But if we already have a pre-computed Shamir share of a random secret R, which is known to the client, then the client can just send a single field element, which is the correction between the random or pseudo-random secret and the actual secret to one server, and the server can just spread the news and send the correction to all servers who can generate Shamir sharings of X. Okay, so these are just two simple applications of linear correlations that we'd like to generate to compress using PCGs. Okay, in the two-party case or more, right? This is really where the new stuff is. Right, so the new results, the new line of work on PCGs really started with the two-party case. I will also talk about the older results. The most basic type of correlations is oblivious transfer correlations. So we want to generate n instances of random oblivious transfer, where a sender has a pair of random strings or bits, and a receiver gets one of these two bits or strings chosen at random. And this is useful for 2PC of Boolean circuits. More concretely, we need a total, in the two-party case, we need a total of 4 communication bits and consume 2 instances of oblivious transfer per AND gate. Okay, if we want to use OTs for 2PC of Boolean circuits. An arithmetic generalization that we heard from Peter about yesterday is OLE correlation. It's essentially the same as OT, but for arithmetic circuits. Something we heard a lot about from Peter is vector OLE, which is in a sense easier than many instances. So it's an easier task than generating n independent instances of OLE to generate one long instance of length n of Vole correlation. And this is motivated by the applications we heard about from Peter yesterday. many applications, a growing number of applications. We have authenticated multiplication triples or unauthenticated triples used in Beaver or Speed style protocols. The authenticated version is useful for malicious security. We have a truth table correlation that we heard about from Elet on Sunday, which is basically a correlated randomness setup that allows us to compute an unstructured function or gate with minimal communication cost. The downside is that this correlation is as long as the truth table of the function. And the correlation consists of a randomly shifted signature truth table. So what we heard from Elet about a more general way of viewing it as an instance of an FSS correlation. And finally, the above examples can be unified under the general notion of an additive correlation, where we have some distribution R, some distribution over n elements of an abelian group, and we just split a sample from R additively between two parties. And these correlations can be also generalized to more than two parties. Okay, so let me briefly review the state of the art that I will give more details about mainly in the second hour. So if we only want to use symmetric cryptography, then we can handle the linear multi-party correlations that I described in the beginning, as well as a single big instance of a truth table correlation. So these are the types of correlations for which we have PCGs using only symmetric cryptography. On the high end, if we use the indistinguishability obfuscation, then we can get a general solution for any correlation, albeit in an impractical way. If you want something that could be practically feasible but very, very slow, we can use general homomorphic encryption technique to implement a PCG for any additive correlation. I will briefly show how this is done, but this is quite easy. This is a generic solution for these natural instances of the PCG problem. This is something that Peter will talk about tomorrow, but we can use, if we have complexity classes such as log depth circuits or certain types of simple correlations, and we use public key crypto assumptions like DDH or Payet, DCR, then from a theory perspective, we can handle any additive correlation that can be generated by log depth circuits. And from a practical perspective, we can do things like Vole, OLE, OT. It's practically feasible, but kind of slow. We'll hear more from Peter tomorrow about it. And finally, this is the new area of Lapland. Using LPN style assumptions, we can generate all of the two-party correlations that I mentioned in a reasonably fast way, and I will give some data points of concrete efficiency. So really, we can, in theory, we can extend this LPN-based PCG construction to any additive correlation that has constant algebraic degree. But if we consider a good concrete efficiency, then we're left only with these two types of constructions, those that are based on symmetric crypto and those that are based on LPN for the simple but useful correlations that are written here. So most of the types of correlations that we need for general purpose secure computation, we can generate them with good concrete efficiency under LPN style assumptions. This will be the topic of the second hour. And in fact, the efficiency of these constructions keeps getting better and better. And again, I will give some data points. Let me maybe just give one punchline, is that if you consider the cases of OT and Vole, or let's focus even on the case of OT, now not only communication complexity is better than the IKNP OT extension, but under plausible assumptions, we have constructions. This is the most recent one where even the computational cost is better than the classical OT extensions. So it's getting to the point where it's kind of a best of all worlds solution for many purposes. Okay, so briefly going over the generic construction from HSS. So we call that an additive correlation takes a sample from some distribution R and just additively splits it into R0 and R1, two additive shares. And homomorphic secret sharing, just as a reminder, it splits a secret X into two shares in a way that allows us to locally evaluate an arbitrary function F on the shares, giving us an additive sharing of the outputs. Okay, this is the dual notion of function secret sharing that I talked about. And given such a general purpose HSS, we can just take an algorithm that samples from the correlation R, the distribution R, sorry, it's not a correlation R, it's just some distribution over an abelian group, using a standard PRG. So we take a short seed, we expand it using a standard PRG into a long pseudo-random sequence of group elements. Now we again implement using a general circuit sampling from the distribution R. So this is just a centralized way of generating an instance from this long distribution R using a standard pseudo-random generator. And now if we have a general purpose HSS, we just implement a distributed version of it. So we take the PRG seed, and the PCG seed generation will just apply the HSS sharing to the PRG seed from the centralized solution on the left. So we use HSS sharing to split the seed into two parts. And now we do a local evaluation of this centralized sampling function F, and we get additive sharing of the output of F, which is R. Okay, so this is a general purpose approach, but it is not concretely efficient. Okay, but in terms of assumptions, it can give us some nice results, nice feasibility results under different kinds of assumptions, but it's not a practically feasible approach. Okay, so I have, when do I need to end? Like, can I take a couple of extra minutes?
Yes, you can take a few extra minutes from the second hour.
Good. So let me briefly cover both all the new results on PCGs in Minicrypt, so using only symmetric crypto. So if we have these linear correlations, so again, the parties jointly get a vector which is uniformly random in some linear space. Think of it as a linear secret sharing of a random secret. The high-level idea of doing it is to reduce the problem of generating an instance of this linear correlation to distributing replicated independent elements from the domain. So think of it as a linear subspace over a field. So think of a process in which the dealer generates uniformly random and independent field elements, and each element is given to some subset of the parties. Okay, so here each field element, so the red is one field element which is given to the first four parties. The green is an independent random field element which is given to the last four parties, and so on. Okay, so we have these replicated independent field elements. That's totally information theoretic up to this point. And now we want the parties to locally convert these replicated independent field elements into an instance of the target correlation using some linear local conversion mapping. Okay, up to this point, it's easy. It's not clear why we need more than a single field element, right, or more than a single color. The reason we need these intricate replication patterns is, again, that we need this security against insiders. So we want this information theoretic game at this point to be such that even if we consider the view of any subset of parties, so the field elements that they receive, it should not give them more information about the outputs of the uncorrupted parties beyond what is allowed by the ideal target correlation. Okay, so in the case of additive shares of 0, the adversary should only learn the sum of the outputs of the uncorrupted parties, given all the replicated field elements that the adversary can see, and this should hold for any number of corrupted parties. Why is this information theoretic game helpful? Okay, and again, so this has a general solution for any linear correlation by considering minimum support code words in the corresponding linear code. I will give 2 concrete examples, but before giving concrete examples, the reason we want to have this replicated independent randomness is that it natively supports a PCG using a standard pseudorandom generator, or you can even use a PRF if you want it to be stateless. And the reason is that now we can take every field element in the information theoretic solution and replace it by a PRG or PRF seed that generates many pseudo-independent copies of the same field element. So we can generate many pseudo-random instances of the same process by just replacing each field element in the information theoretic solution by a seed of a PRG in the computational solution. Okay, and to just give an idea of how these solutions look like, so if we consider the case of generating many instances of additive shares of 0, we can use this tournament-based approach. So a tournament is a click where you have some direction of each edge. So take any tournament graph between the parties. And now, this is the target correlation. So we want the parties to end up with R1, R2, up to R6 that are random subject to the restriction that they add up to 0 in some abelian group. And the solution using replicated independent randomness is to assign a random group element to every edge in this tournament. So each random field element or group element here is given to exactly 2 parties. And the local output that each party computes is just the sum of the incoming elements minus the sum of the outgoing elements. Okay, and again, the reason this is secure is that, and you need all edges because security against a set of parties, corrupted set of parties requires that the graph you get by removing the corresponding nodes and the incident edges is connected. Okay, this is why you need the full graph, and it has quadratic complexity in the number of parties, and that's optimal for the information theoretic game. The case of Shamir shares is more involved here. If we want to generate degree D Shamir shares, we need n choose D replicated elements, where each is given to a set of n minus D, a distinct set of n minus D parties. And the idea here is that with every element, okay, so this is like a red element, green element, and so on, we associate a valid share vector, so a valid degree D polynomial that evaluates to 0 or the entries of the parties who do not own this field element is 0. So now if we take the random element, the red element, times this share vector, this can be evaluated by all parties. Obviously the parties who hold the red element, but also those who don't, because we fix this share vector to 0 in the corresponding entries. Okay, so we add up, we take this linear combination of these fixed share vectors, and we get something that everybody can compute and has the right secrecy property. Okay, and to give just a quick data point about concrete efficiency, again, it's fast, it uses only symmetric crypto, but it does have this N choose D overhead. So this is a data point of generating a degree 3 Shamir shares between 7 parties, million instances, short seeds, fast expand time. It's practical unless we're talking about, a big number of parties. So let me just briefly advertise the recent work from last TCC, Ben Hamuda, Boyle, Gilboa, Ishai, Levy, and Ariel Nof, where we're motivated by efficient MPC with share packing, in which we anyway have some gap between the security threshold and the degree of the polynomials, and then in this case, it turns out that you can improve this and choose the overhead, and get much better symmetric crypto-based pseudo-random secret sharing solutions. It's based on a combinatorial object called a covering design. The construction is not completely tight in the sense that the covering design is necessary for a solution, and our solution is a factor of D+1 away from optimal, so there is still some gap, but it's not far from being optimal for the information theoretic game that I described. And these are some data points. So if you look, this is the classical N choose D, so-called CDI, pseudo-random secret sharing. And this is what we get by settling for a security threshold, which is smaller than the degree. This is the degree. Think of this as the degree of the polynomial, and this is the security, and this is the security threshold. We get a very significant savings, which can make this approach practical even for a big number of parties. Okay, I guess that, let me just, okay, sorry, I'm running out of time. Let me conclude this part by telling you something we can do in the two-party setting based only on symmetric crypto. And this is the generation of a single big instance of a truth table correlation. And again, truth table correlation is just a randomly shifted secret sharing of a truth table together with a secret sharing of the shift amount. And we also have a malicious secure version where we multiply this by some secret. So I'm running out of time, so I will be very brief here. And let me just say that a distributed point function, which Alette described in detail how to construct, you can think of it if you take the point function, where the A value is random and B value is 1, then you can think of it as a PCG for additive shares of a long random unit vector. Okay, and now if we want to generate a shifted truth table, we just need to multiply this secret shared random unit vector by a matrix consisting of all shifts of the truth table. So it's a public matrix times a secret shared vector, which we can do locally. And you can use FFT to make this computation using the fact that this matrix is circulant. You can make it quasi-linear in the truth table size, but it's still something which, so it works. There are different trade-offs that you can get, but unlike the FSS gates approach that Alette described for simple and useful types of gates like equality, relo, and so on, this approach has the advantage of applying for every gate, but it doesn't scale. So something in the computation has to be at least linear in the truth table size, so it does not scale to functions that have, to gates that have, say, even 32 input bits. So that's it. This concludes the first part of the talk. Sorry for running over time. Yeah, so if there are questions.
Yes, so there are some questions. One is, can the seeds be reused in several consecutive computations? So like if two parties are doing several multi-party computations with other parties, different parties, can the seeds be generated only once?
Yeah, so you can generate the seeds once, then you have a local expand where you can generate, say, 1 billion copies. If you have the right parameters for the PCD, you can generate 1 billion instances of authenticated triples. And then you can consume them by different, as long as the total number of gates you're evaluating is bounded by 1 billion, you're fine. So you can consume them by multiple MPC protocols. I will talk about a stronger notion called the pseudorandom correlation function that doesn't require you to do this work of locally expanding everything and allows you to generate more and more things on the fly.
So there's one more question. So in the context of tournament-based generation of secret sharings of 0, so for creating additive secret sharings of 0 over Z2, it seems that you get the dining cryptographers problem. So do you know if there is a name for a generalization of this?
Yeah, I don't know the name, but it's a simple generalization, yes.
Oh, that's it.
Okay, thanks, Yuval. We'll have to stay tuned for the second hour to hear more about PCG constructions. So we'll take a 15-minute break now, and then we'll return for your second talk.
Thank you.